you for coming back in. And I'd like to start with the basic things about quantum computing. So, how would you explain qubit to someone who knows only knows classical bits? Like, what is qubit and how can we visualize that?
Yeah, that's a good question. So, uh, a qubit, interestingly, can be quantified as anything. Like you can actually simulate qubits, right? I've actually done this, and then I call them new bits, and then so you can simulate qubits in classical computing, and then it's essentially just mathematical function, right? It's essentially a qubit is just a measure of related to information theory. It's a measure of compute, and then so a qubit is a non-linear function, which I'm assuming that we'll get into later. But
Right.
it allows you to do like non-linear search very efficiently, and then that's like essentially what a qubit does is it crunches non-linear algorithms, whereas most of your compute crunches linear equations.
Right. So I came across some term or some text which was explaining qubit something like it is a kind of probabilities Bayesian probability thing. Like it will be existing from imagine 1 to 1,000, and it will be in the variations of like in some kind of graph we can visualize it like some kind of that.
Oh,
So
for sure. So I'm assuming that they're referring to like HDC, and that's where
right,
you come into it a lot, like hypervectors. And then so
right.
if you're like trying to relate out or utilize qubits, like
Hmm.
to actually like compute, that's a good way to think of them, right? Like as hypervectors. It's kind of qubits operate along those same things. Like if you break down how hypervectors work, it's kind of like an instantaneous process, right? Like it instantaneously finds an answer, and then you find from there it'll like instantaneously find like 82% or 85% probability. That's exactly like
Right.
the same type of thing that a qubit does. It's making those more instantaneous calculations, and it's doing that utilizing dimensionality, right? And so where you bring up like 1,000 dimensions, that's what it's doing. It's like computing essentially across the probability of 1,000 dimensions at once, and then it's computing
Right.
the probability of one
That's
thousand
really
dimensions.
awesome thing to imagine, like thousand things at once. Yeah. So,
Yeah,
uh, what's the difference between quantum entanglement and the classical correction?
for sure. So this is an interesting question because there's actually a research that came out like a few days ago with regards towards quantum entanglement specifically, and what um, the research is showing more and more and more and pointing towards is that there's a possibility that the quantum entanglement is essentially like another compute function, like another form of compression um, related to classical physics. More and more, what is coming out as far as research is that our understanding of classical physics as a whole, it has flaws and holes in it. And so, talking like the most forward-thinking physics, it's like the holes are coming in this area specifically. Like, what is quantum entanglement? Classical understanding is that quantum entanglement is kind of like this spooky from a distance, spooky magic from
Right.
a distance, right? Is how we frame it. And then the more that you get into it, it's um, there's the probabilistic aspect of it is probably related to compression, and then so related to compression distances between um, two entities, like a unit of measurement. I think would be a good example of or a way to think of what quantum entanglement could be, but um, like within quantum entanglement, measurement itself causes collapse, right? So, which is
Right.
interesting
Yeah.
within that. So it's interesting to think of it that it could be related to a unit of measurement, but also that measurement causes collapse. So there's something that like there's definitely gaps here that we still don't understand fully.
Completely right. So, why are hybrid quantum classical algorithms like QAOA critical for NISQ era devices?
Yeah, classical and quantum algorithms to me are like that's the most interesting and fascinating field within this, right? And that's what we're
Right.
finding out more and more. So to me, the basis of neural networks and deep learning as a whole is the mixture of linear algebra, like linear and probabilistic math, and
Completely right.
combining them together and the combination of the two. Uh, and then for a long time, like it was quantum physics versus relativistic physics, right? We have these kind of like versus debates a lot, and then
Right.
what it is that now is like, well, it's a continuum. It's not a versus. Like it's um, quantum physics at the beginning of the continuum, which leads into an emergent property of relativistic physics, most likely. Like and um, that's how the algorithms work, right? Like that's the progression of a classical algorithm utilizing quantum mechanics. And it's the interesting thing is that we're finding more and more that you don't need quantum hardware in order to perform quantum functions. So like that
Right.
means like there's not a gap there. There's a misunderstanding with regards towards our
Right.
understanding.
That's awesome. So, what's the biggest flaw in current quantum error correction frameworks, and how we can address that?
For sure. I mean, the biggest. I mean, absolutely. The I mean, the two fundamental questions with regards towards physics are uh, the same to me. Fundamental questions that have been around for 100 years now. What is gravity and what is time?
Right.
And that's the two. Like, I mean, that's where we're at, honestly. And then so.
Hmm.
Um, Playing around with those equations, and then where we're at now with computers and being able to simulate these things on large scales is we can now run simulations where we can take guesses and stabs at that. Like, for example, like, I mean, I can't, I would be proposing like a unification of physics if I was like, here's the full continuum, but I could run experiments to do that, and the technology now exists for that, whereas it didn't in the past. And I think that's what
Right.
the key difference is now is like we have enough compute to actually play around with these things and to actually come to conclusions that we
Completely.
couldn't draw before, whereas before it was just, oh, this is in the realm of philosophy.
That is really awesome. And what is the basic intuition behind the back propagation, and why it's still dominant?
Yeah, back propagation to me is fascinating, right? I'm glad that you bring it up because a lot of people they bring up back propagation as a negative thing within the space, and then
Right.
so the way that our brain works, like the way that the human brain works, there's no back propagation process. Back propagation is very straightforward, right? It's let's say that we take a problem of 2 plus 2, and then I put an output, and the output is I say it's 5, and
Right.
then you say no, the output is actually your out response was 5, but the output is 4. And then
Right.
back propagation would be taking that, like that, what you just taught me, and then running that across the weights. And then so, okay, the correct answer was 4, and that's what's getting back propagated, right? And
Right.
then so next time I do it, I'm like, well, the answer is 4 because that's I learned, and then so that's the like kind of like
Completely.
how that works.
Yeah.
But the human brain doesn't do that. Like there's nothing within like neurons only operate in a feed forward mechanism. So you feed information forward,
Okay.
and then so people often knock a neural network within that because they say that it's not human, right? But to me, when we look at these things, I think it's important up front to differentiate intelligence as a
Hmm.
whole from AI intelligence, from human intelligence, from elephant intelligence, from octopus to
Completely. Yeah.
dolphin. Like it's all
Right.
different, right? And then
Completely.
an octopus thinks complete like an octopus has a completely different like an alien brain structure. It's
Right.
a distributed brain essentially. Like I
Completely.
would
Yeah.
like if I was to build a perfect model, I'd model it after an octopus, not a human. But I would include back propagation within that. Why not? Right? Like it's
Right.
I don't see it as there's no detriment to it. Like people are just like, well, it's not like the human brain doesn't do it. Sure, like it doesn't do it, but if I could, I would. Like why would I not? If I could
Right.
like program myself to have that algorithm, I'd take it. Like if it was a choice, like if like you can have back propagation or not, I would choose yes. Why not?
Right. Do you think that back propagation thing in the human brain will be possible with the neural link in the future?
That's a good question. So I that's a scary question. I, I,
Right.
to me, that's the scariest question. And I guess that's, I mean, the place I honestly where I start with all of this, right? Like I guess like where does my like interest, like my purest interest along these lines peak, and I guess it's there, right? I start with um, my first rhetoric class in college. I'm learning these things. I'm learning about like how marketing works, kind of like on these levels, and what they're learning about the human brain. And I learn more and more that there's an extreme possibility like the human brain is very like robotic, and like
Right.
and very like algorithm driven, like and if you could essentially like via like electricity, if you understand how the algorithms work, like you could control like the human brain just like anything else, which means that
Right.
like theoretically you could rewire it like overall. So like I think it's 100% possible. All of that Neuralink and diving into biology overall, it scares me because I'm of the like belief that a lot of this is computational, that like your brain is a computer, and
Right.
that
Yeah.
like it's algorithm based, and then so like it just scares me like playing around with that. So it's
Completely. Yeah.
scary.
So how do transformers differ from traditional RNNs or for NLP task?
That's a great question. So a fantastic question. So the biggest differentiation between transformers and everything else that comes before it is what is in the most like the title of the most common research paper around it that everyone talks about, right? Attention is all you need.
Right.
And then so transformers introduces the attention mechanism. It's the introduction of that. So the transformers does a few things differently. Like what you mentioned, one of them, backpropagation, and then the second one is the attention mechanism in and of itself. And then the attention mechanism is very straightforward, right? It's essentially if you have a sentence and then it's rather than just saying you can only pay attention to the next token in the sentence, the attention mechanism allows you to focus on the sentence as a whole or certain aspects of the sentence. It allows you to move the attention mechanism essentially. And drawback of that is it's mathematically computationally expensive.
Right. So did you replicate the diffusion model by any chance, anytime?
Yeah. So I have a lot of experience overall with diffusion. To me, diffusion is fascinating overall as to how it works, right? Because you're taking
Right.
like diffusion. To me, it's different than AI. I think of and I classify in my head
Mm-hmm.
diffusion and machine learning and AI as two different things. Like they're not they're like two different technologies. Diffusion is just like purely reliant on the laws of relativistic physics, right? Like it just
Right. Yeah.
it,
Cause I never understood diffusion, what that exactly concept is till now, and I'm still
it's
trying to understand that, like getting the proper intuition how that works, and that really fascinates me.
yeah, no, I mean, it works just like literally because of just pure physics, right? That's
Pure physics,
exactly
right?
what's going on. Like it's just um, heat transfer, but and the laws of heat transfer, but within digital spaces, and that's like
Right.
that component intrigues me a lot, right? And that's been like a lot my major focus a lot for like a year or so or 2 years, like trying to tell people like there's laws of physics in these digital spaces, right? Like I can
Completely, yeah.
take a digital space and I can replicate diffusion in a digital space, and
Right.
I can only do that because laws of physics exist within these digital spaces. And
Completely.
then I don't know what that means, but we should explore
Completely.
it
No,
more.
that does make sense. So, the with the same concept, there was one argument that if the reality that we are living in is that simulation or it is real. So, what's your take on that?
For sure, yeah, no, I mean, so my like broad take on that is like, I mean, Elon Musk's argument overall is very strong, right? That if the probability or the possibility exists, like if um, so essentially, if simulation technology gets advanced enough, then like it's almost a certainty that we live in a simulation just because of the advancement of the technology, right? So. There's that argument overall. Um,
Right.
Also, like there's different, but I think it's also important to understand and to like recognize like there would be different levels of simulation and like what exactly is like simulation and what would be the purpose of the simulation overall. Simulation theory, just like saying it's kind of like scary to talk about up front, right?
Completely, yeah.
But like once you kind of like you peel it back, it's like so up front there's a high probability, like at least a probability that exists that simulation theory is like there's some practicality to it. It doesn't go away, right? Within physics, like
Right.
no matter what you do, you can't get it out
Completely,
of
yeah.
it. So operating within that framework, it can be quite like a little bit scary up front, but once you peel that back, it's like, well, it's not necessarily scary. It just means that like essentially like the universe could be like is a computer, like or operates like a computer within that, like and well, why, how? There's still a lot of questions that would operate within that framework.
Completely, right. So when you replicated diffusion model from paper, how did you debug the unstable training dynamics?
Yeah, I mean that's a fantastic question. That's a super good question. So to me, like I flat out like the very first thing that I did, like when I was playing around with diffusion, I played around with diffusion and swarm algorithms both at the same time, and then just understanding like the dynamics of what fusion does and how it works in a physics process. To me, my first assumption was that you can just do the same thing with swarm algorithms, and then escape those like a lot of
Ah,
those
okay.
like training process like those problems in that training process, right?
Right.
And then so like that's how if I train a diffusion model, I'm taking swarm algorithms and I'm training them to act like diffusion, and to me that works
Okay.
very well. Like
All right.
like how do you like I run into the same problems like and even just thinking about the math of it that you just brought up when trying to
Completely.
train a diffusion model, like it's counterintuitive to train a diffusion model, like you shouldn't be able to. So there's
Right.
something again, and that goes back like there's something missing with our understanding of physics for these things to actually work.
Completely, yeah. Because that does challenges the understanding of physics that we are right now. And yeah, how do neurosymbolic architectures merge logic rules with deep learning? And what's their limit for scaling those?
That's a fantastic question. So everything boils down to representation. Like that's the base answer to this question, right? Um,
Hmm.
Language itself, the words that we're using, like the fact that we're using like English as a language, it's a representation. And then so if I use English to say the word cat, that's a representation of the word cat. And that's where I like to start with like cat because that's a simple concept, right? So
Right.
within like, that concept, then we take this and then you take it into the philosophical realm, right? And then like Plato brings up like in this concept you have Platonic forms, and then so uh, within this concept of cat, there would be like and there exists according to Plato a perfect form of cat, and then so literally everything else that we are basing off of is a representation of this perfect form of cat. And then
Right.
um, when so if that theoretically then we are concerned then with giving the model the perfect form of cat. And then if we
Completely.
give the model the perfect form of cat, then every sub instance of cat therefore is enveloped within that. Like we don't have to give it every form of cat because every form of cat is a representation of the perfect form of cat. And then so
Right.
we just need to give it the perfect form, and then everything else falls
That is really nice way to look at it.
through.
So, why is linear algebra foundational for both quantum and quantum computing and deep learning?
Yeah, like I mean, so linear algebra is like mathematically elegant, right? It's the easiest part of math to understand because
Right.
linear algebra is very straightforward. Like it's linear, um, it's linear progression. 1 plus 1 equals 2, 2 plus 2 equals 4, etc. Right? 2, 4, 6, 8. Like it always a linear progression. And that's how computers work. Like how they've worked overall, etc. So it's a framework that humans, like the human brain, seems to I would say go so far as to say that it's most likely that the like base logic or base like algorithm of the human brain is like linear based, right? Like it's just like
Right.
for some reason, whatever reason, like when it comes to linear equations, our brains understand linear equations very well. It's just we're very efficient at linear equations, and then so
Right.
I think that a lot of it boils down to that overall, right? So within neural networks, you need and always you cannot get away from the blend of linear algebra plus some sort of probabilistic math. Like you always need the combination of the two, and then so linear algebra is always your base, right? And it's like you always and you can have like even like 2% linear algebra, but you always need like that 2%. You can do it the other way too, right? Like you can go like 98% linear algebra, but then you always need 2% probabilistic math. And then so to me, it's again that blend and that combination. Like what makes linear algebra special? I don't think anything makes linear algebra special beyond the fact that like our brains are attuned to linear algebra. So we're
Right.
gonna like
We think
prefer.
in the patterns, some kind of linear patterns, right?
Yeah, exactly.
So, what role does calculus play in optimizing neural network loss functions?
So same exact thing, right? Like so, I mean, to me, like calculus is the most simplistic way that I can put this is to me, I think that what goes on with models within the universe itself overall with a lot of this is you mentioned it at the top, compression, right?
Right.
And then what happens is that you take noise and whatever noise is, and then you compress the noise,
Hmm.
um, and then by reshaping it, and essentially you need to utilize calculus to reshape, and so that's where that probabilistic aspect comes in, the calculus aspect comes in, where you're just taking random noise, random chaos, and then you just shape it, and you shape it probabilistically, and then eventually a shape, a signal pops out, and then
Right.
uh, from there, like once you have like okay, here's something meaningful, then you can employ the linear. Then you go linear, right? And then the linear algebra comes in, and you're like, let's trace this back and let's figure out what happened. But your linear algebra is never gonna get like that pop, you know, like so
Completely
that's why
right.
they're both need. That's why you need both.
Right. So, how does no free lunch theorem impact hyperparameter tuning in machine learning?
Yeah. So that is huge, right? Like, and I think like a lot of people they ignore this equation overall. Like most recently, right? Like there's a like Stargate and everything coming out around that, like that
Right.
whole $500 billion investment, and the logic behind that is that we're just going to scale up infinitely, right?
Right.
But no free lunch, and so we can't scale up infinitely. Like you run into um, all kinds of like there's like any time that you try to scale up,
Mm-hmm.
you run into laws of physics and multiple
Mm.
laws of physics, like like in multiple different ways, and then that's what we're already running into within this equation, right? You can't um, scale up. You can't essentially we can't get and squeeze compute out of more compute just by scaling up infinitely. No free lunch. To do it infinitely, there's always
Mm.
like diminishing returns. We can't do it with data for these same reasons, etc. And it's just, I mean, it's literally it's built into communication. Like uh, there's nothing that can escape this equation. AI itself can escape this equation.
Right. Okay. So, explain the role of Lie algebras in quantum gate representations.
Of what algebra?
Lie algebras.
Oh, light algebras. Yeah, yeah.
Yeah.
So light algebra is um, to me the most fascinating and interesting part of um, physics that we're running into,
Mm-hmm.
and so light in and of itself as a kind of like a discrete storage unit, right? Like like scientists have been able to like utilizing just flat out linear algebra and what we know about these things to literally write data to light itself, to treat it as a storage mechanism itself, and that goes kind of like back to like that whole um, compute. The universe is compute based, compression based, etc. Like all of that functions within that model, right? That light
Right.
is in that instance then like the ultimate form of compute. That anything outside of that, we're just like brute forcing. Really, is like kind of like the bottom line, and like the essence then like the purest um, form of mathematics, of physics, etc. that you can get into is light and light equations.
Okay. That's really awesome. So, topological quantum computing uses abelian anyons, and how do they enable fault tolerance?
Yeah, that's a that's actually a really good question, right? So, um, like so first of all, explaining what topological computing is, like essentially it's just utilizing shapes, right? And then like
Right.
I'm huge on this research at the moment, and then
Hmm.
essentially if you take a data set, let's say Harry Potter, right?
Right.
Harry Potter has a shape, the book, and there's a shape of this data set. And then so if I just essentially like, if I give the model the shape of Harry Potter, it will um, know and understand um, what it like word for word, here's the book of Harry Potter. But all I did was just give it the shape. I didn't give it the
Right.
words like anything else. I'm just like, here's the shape of it.
Hmm.
And then so that's what we're dealing with when we're dealing with topological computing, is that these models are dealing with shapes of data, and then
Okay.
reshaping and formulating, and within that it goes back to dimensionality. So a lot of this is compression and dimensionality. And then so dimensionality allows you two things. You can expand dimensions and compress dimensions. So I can take, for example, like a two-dimensional image, and then I can blow it up into hyperdimensional space. So like say
Hmm.
4 dimensions, 5 dimensions, inconceivable amounts of dimensions, 10 dimensions, etc. And then this will change the shape. And also too, if I take a two-dimensional object and I bring it down into 1 dimensions, that significantly changes the shape as well. It reduces the complexity of the shape. And then so I can do that both ways, right? I can stretch this data, change the shape, and then I can also run calculations based off of the changing of those shapes, right? So, like the differentiation between the shape of a data in 4 dimensional space as opposed to 2 dimensional space, as opposed to 1 dimensional space, and then running calculations in between those. And then so answering your question very specifically, when we try to, so our classical understanding and the common way of doing these things, like of measuring these shapes and the classes in between these shapes, is kind of how we break this down, is Hamming distance. And then
Hmm.
what you bring up within that is a common thing that happens within Hamming distance, where if I take that two-dimensional object and then I blow it up into higher dimensional spaces, it distorts that shape. It changes the shape, as I mentioned. But then so within that, those distance equations no longer work. Like my Hamming distance equation breaks because I'm distorting the distance, right? And then so
Right.
that's the common problem. Like how do you measure around that? How I measure around that is essentially probabilistic math,
Hmm.
and recognizing, and then to me what I just laid out, right? So
Hmm.
recognizing that you have a 4 dimensional shape, which is a different shape than a 2 dimensional shape, which is a different shape than a 1 dimensional shape, and that gives me a starting point. I can utilize the difference between the shapes, and so 2 dimensional space is going to change it, it's going to distort it, and I know it's going to distort it. I don't know how much it's going to distort it, but the difference between 2 dimensional space and 4 dimensional space is exactly how much it'll distort it. And then so if I train the model on that, then it knows. And like I found that works out very well. I haven't found any flaws in it so far.
That's crazy to imagine, man. And
Yeah.
can category theory unify quantum and classical machine learning frameworks?
Yeah. So yeah, exactly. So category theory to me is very interesting framework within this, right? It kind of ties within to what I was just talking about overall. So within a data set, you can essentially categorize or understand a certain part of the data set by going through and it's called like an involution cycle. You can classify the data set, right? And that's essentially what our understanding is, that like hyperdimensional computing algorithm. That's it. That's how they work. Like is that they're essentially like they're taking let's say Harry Potter as our data set, and then they'll go through, and I have 10,000 dimensions, right? It'll classify and categorize those, like Harry Potter, into what it thinks and understands as those 10,000 dimensions. And then so that's like essentially how it's learning in this instance, right? Turning that signal, that noise into actual signal data. It's shaping that individual data and shaping it into categories in this instance. And then within category theory, like the kind of the number one rule within that is, so I can do that, right? I can take Harry Potter, I can give it to a model, and it'll learn the shape of it, and then let's say it comes up with like 60% accuracy as a result of that. And then so I do it again. It's not going to improve. It's going to improve inherently less than 60%, like 55%. It might improve the next time, right? So I might go from 60% accuracy to 80% accuracy, and then
Completely.
and the next evolution I go, it will never improve more than 50. It will never hit 55%. It'll always be less. Always diminishing returns within that categorization.
Right. So, what's your opinion about the paper Lars model unlearning paper? So, is it truly possible to erase data from LLMs?
Yeah, that's I like. So I haven't read like that particular paper. So I don't know exactly what their method is or what they claim within that particular research paper. But like I haven't seen any specific method that has come out in existence whatsoever where a model is able to unlearn data. And why that
Right.
is, I don't like. I can't fully explain that to you. I can like. I've actually in my research I've actually had this recent conversation, right? So I can train and I'll take a neural network and I'll train it on Harry Potter, and
Right.
I train it and let's say it gets 60% accuracy, right?
Mm-hmm.
And then I reset that model, I reset the weights, but it's the same model, but I'm just like I'm resetting everything back to zero, but like and then I do it again, and it'll get 70% accuracy, but I reset everything to zero though. So,
Hmm.
but there's like something like a ghost memory gets retained in
Right.
there, right?
Right.
Some
Yeah.
sort of data gets retained, and like
Right.
that's a part of like that's a very big missing element that we still don't understand yet around that.
Hmm.
There's something that gets retained in between those informations.
Completely right. So, I came across this term, multimodal large language models. So, what are those and why are they trending right now?
Multiple large language models, you said?
Multimodal.
Oh, multivariable. So like multivariable. Like so, my like the way that I equate that out. There's two different things. Like there's so essentially I equate. It's basically the same thing. Mixture of experts, right? And then a mixture of experts across different domains. So you can have mixture of experts, meaning across the same exact domains.
Mm-hmm.
So you have let's say. Um, you have a mathematical problem. You would have like 5 individual models, and then each one would be trained in an individual subject of mathematics. So like one would be like trained in addition, one subtraction, one multiplication, etc. You combine those together, and then their response is essentially the output that you get within. And then so that's within a singular modality. Taking it a step further,
Mm-hmm.
you can do that same type of logic across modalities, and that's kind of like solving the problems that we are still running into a little bit within these problems. So I guess to take it a step back before answering the question fully, when you let's say you prompt ChatGPT for an image, right? You're not
Right.
actually getting the image from ChatGPT itself. You
Mm-hmm.
get it from Dolly, from a
Ah.
connected model to ChatGPT, and then so
Right. Yeah.
ChatGPT itself like makes a call to Dolly, and then
Right.
it
Right.
retrieves
Right.
it back.
Okay.
But what would be better is if Dolly was integrated as
Hmm.
one of those layers of ChatGPT, right?
I thought it
But
was
then
integrated, so it is not. Okay.
yeah,
Okay.
yeah,
Yeah.
for sure. But so
Right.
that's like what we're working towards is trying to get that like, and that would be like the ideal situation, and most likely like the ideal LLM, like having all of those modalities actually integrated, like
Hmm.
probably important.
Right. 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 So, can synthetic data replace the real world data sets?
Yeah, so fantastic question again. Like, so I think that like when I don't like there seems to me, and this is just my personal opinion on this. There was like a like big push to knock synthetic data for whatever reason for like a year, and then but like all of my research that I've come has stated the opposite, and I've stood behind it, for like 2 years that like synthetic data is um, essentially equivalent to real data, and then now you're like more and more like studies are coming out on that side, right? That there's literally
Right.
no difference between the two, and then more and more it's again this we're finding out that it's the shape of data, right? Like and that like it's essentially that the models aren't actually learning the data itself. Like they're learning shapes and objects and pieces within this data, and then we're learning more. What exactly does that mean, and how do you do that within data? So we're learning that there's a different like high quality data, less repetitive data, um, more surprising data, uh, things that are more meaningful in general means better data, and that data tends to actually be more valuable for the models overall. Like it's kind of like almost or just as important as compute, right? Like it's that equation that you can pull. Like if you have very good and high quality data, it's just as important as very good and high quality compute.
Right. So, what is the biggest bottleneck in deploying tiny machine learning models on the small devices like edge devices?
So like I think like the biggest thing within that, like people don't understand, like they don't have this concept of exactly how large language models are, right? That's the bottleneck. So a we think of like all like I'm not even gonna go towards like ChatGPT. I'll go towards like so Llama 7B, right? Like Llama 3 7B. Like that's a very common model. Like like 99% you would not be able to run that on your computer undistilled. And that's a 7B model, like Llama 7B, right? There's nothing like, I mean, there's 70, there's 13B, 70B, 400. Like, there's a lot
Right.
bigger models than that. Llama 7B is a very small model
Completely.
overall, right? But even that model is too big to run on your computer, right?
Right.
Like as a general rule.
Completely. Yeah.
As, yeah, like as a general rule, you can run like Gamma,
Hmm.
the phi models, the small
Hmm.
LLM models,
Hmm.
and then so those are the models, and those are the like those are what you can run right now. So it's just a matter of how do we scale that down from there, right? Like uh, you need so in order for like a neural network to work, like and deep learning to work, it operates essentially off of complexity theory. Um, like we're taking complex systems and multiple complex systems, and we put them together. In order for complexity theory to work, you need a minimum amount of complexity, right?
Completely.
And then so like that's where like we're kind of running into like what's the the challenge, and it's a beautiful challenge, an intricate challenge of how do you make complexity smaller and smaller and smaller, and you can, but it's engineering problems. And it's all algorithmic, right? Like how do I
Right.
make more
Completely
complex
right.
algorithms that take up less memory?
Right. So I came across some term which was telling that there is some kind of compression in the uh, networks or large language models, or I have no idea what compression in that large language model or neural network means. So yeah, I'd like your take on that.
Yeah. So I mean, compression is exactly what you think of it, right? Like environmental compression, where you like you're just literally like compressing or squeezing the data. So if you're compressing the data, that's exactly what you're doing. Like if it's
Ah, okay.
and to make it more visual. So let's
Mm-hmm.
say that you take in a data set, and let's say that you take in you take it in 3 dimensions. Compressing it would be compressing it to 1 dimension. Like that's compression, right? Like you're
Mm.
removing dimensionality out of the data set, and then
Okay.
you're changing the shape of it. It's a 3 dimensional shape. You're literally like taking a 3 dimensional shape and you're making it flat. You're compressing it, and then so that's what like compression is in these spaces. And then so when it comes to physics overall,
Mm.
compression is just a natural portion and a natural part, a natural occurrence within spaces that occurs.
Mm.
So compression naturally occurs, right? Stars form, the universe forms because of compression, because compression is a natural thing, right?
Completely right.
It, yeah, like compresses matter together, and then that forms planets and stars, and like we're all being like gravity is compression, right?
Yeah.
We're all
Completely.
being compressed, and then so same for an LM model, and that's but like the logic being that um, compression is like probabilistically your most basic form of compute. Like you can uh, get data out of pure compression. And then so going back to our discussion earlier, right? Like if there's platonic forms of everything, and then so if there's a platonic form of data, then perhaps compression is the platonic form of data itself. That
Right.
like that's where we get to our compute itself. Like uh, compression is the most basic computer that could possibly exist.
That's awesome. So, what are TPUs like GPUs versus GPUs, and explain the trade-offs of using TPUs versus using GPUs for large-scale training models.
Yeah, for sure. So very good question. So GPUs are a graphical processing unit, whereas TPUs are tensor processing units. So just a different formula and a different um, architecture and hardware overall.
Okay.
So GPU, like the simplest way to put this overall, so like right now with computers, we deal with like multiple core computers, right? Like we're dealing my computer is like 16 cores or something like that. But previously, like before multi-core computers, like you had Pentiums, right? Like Pentium 1, Pentium 2, Pentium 3, 4.
Completely right.
And those like were all one single core. And
Single
then
core, yeah.
so and then um, when a GPU came along, like GPU, like in the 1990s, was revolutionary, right? Because it's like you have one core, and
Mm-hmm.
then GPU is 1,000 cores, like at that
Right.
time, and then so it's like uh, one core compared to 1,000 cores is extreme, and then so like computers didn't take advantage of that for years, for decades, right? Because it's like it's like computers are one core, so they weren't built for GPUs, and
Right.
then computers start becoming like dual cores, and then four, eight, etc. And then so as computers start getting more cores, then you get programs that are actually designed to take advantage of these more cores, and
Hmm.
then that's where GPUs get like they blow up, right? Because that's exactly what they
Right.
do. Is that they're like literally all they are. So a GPU is a CPU, but just with like a bunch of little cores. It's the exact same architecture overall, just like tiny amounts of core, like tiny like instead of 8 cores or 8 processors, it's 2,000 or at this point like 10,000 processors all at once, right? And then so TPU is a completely different step from that. It's redesigning and reshaping the architecture and the hardware of a CPU. It's like like it's a different shape overall than a GPU. So uh, I look at TPUs as an advancement of the GPU and of the
Right.
CPU, right? Like so, like a TPU is it's a replacement of a whole computer, and then it allows you to customize the whole computer in
Right.
ways that you wouldn't be able to and can't with just a separate CPU and a separate GPU.
Right. So Nvidia launched something like the little box. So is that a TPU? Ah, okay.
The the little box. That's a good question. Yeah. So the little box that's utilizing a TPU, right? So advancements and a lot of that is so a lot of that is software advancement. It's coupling that software with the hardware, right? So
Okay.
with the TPU, you're essentially like building your own computer from the ground up. Like you're building your own CPU and GPU,
Hmm.
and like kind of fusing them in a unique way, and that's how they're able to get what they're able to do in that little box, right? And that's like that little box is like the first step that you see within this. Like quite honestly, like I think in 10 years, like Nvidia won't have a monopoly, right? Like people don't understand. Like once it's more widespread that like how easy it is to build these TPUs as opposed to GPUs, like
Right.
you'll have a lot more companies that'll spring up doing it
Completely,
close to
yeah.
just NVIDIA.
Right. So, what inspired you to blend into the research, then coding, and all these quantum things, and as well as teaching on YouTube as well?
Yeah, for sure. So to me, the bottom like it's just like what kind of propels me forward is just the engineering mindset, right? Like my base mindset is always engineering. So if I ever come across something like and like computers fascinated me since I was a kid. Like I just took them apart and put them back together since I was a kid. And then so if I ever run into something where I don't understand it, that triggers my mind. Like oh, that's a new fact. Like I want to learn more about it. And then so
Right.
computers and quantum mechanics have just been those two tracks like my entire life. And then so that's kind of just how I got into that specifically. And then and answering your question very honestly and very specifically with regards towards like teaching with YouTube and how I got into that. So for like the last 5 years or so, like I have two kids, and I've wanted to um, not be as involved in my IT career overall. I've had a very good career overall, right? And I
Completely,
make
yeah.
in my career like very good money, but it's um, with very good money in a IT career, it's always a lot of time away from home and a lot of time away from your family on things like that. And so I want to build my life, and so I have built my life on the exact opposite of that, right? Like just being there for my kids is
That's
far more
really
important to me at this point.
completely, yeah. Being there for your kids is really big thing, man. Yeah. And what's a research paper that changed your perspective about all things like AI, quantum, and all? Is there any specific research paper that you like, or there are a lot?
Yeah, I mean, it's just something like that. My answer to that question changes like on a daily basis. Like, right, I don't think I
Right,
would do it
right,
justice like to say like an
right.
individual one. I like to me it's all like this just great journey, right? Like I couldn't and I wouldn't know what I know, and I wouldn't be able to do what I do if someone hadn't researched stuff beforehand. I'm standing on their shoulders, and we're standing on the shoulders of Isaac Newton, who's standing on the shoulders of
Completely.
Euclid, and it's just like all like building together is how I look at it, right? And like that's
Right.
the most beautiful part of it overall to me. It's just like
Completely, yeah.
that building blocks.
So how you stay updated with all these papers? What are like archive, or what are papers are they? Like which are sources? What sources you read papers from, and how you stay updated with all the knowledge you have?
Good question. Yeah. So like Archive is the best resource, right? Like archive.org, hands down, and it's
Right.
like Archive is hosted by Cornell University, and
Right.
then so with regards towards both physics and AI, Archive
Hmm.
is the place to go.
Right.
And then also like if you want like they have new research papers daily. So like if you like the best resource, absolutely. Like if you want to be the most proactive, just go to Archive, whatever you like physics, AI, computer science, etc. And then just read the papers that came out that day. Other than that, like next step would be to, like distilling from there, like news groups, and then like to me, like news groups and LinkedIn are like the big ones. And then I just noticed like if certain papers start getting talked about within my news feed, that's when I pick up on them. And then to me, like the very first thing that I do within that is if a paper starts getting talked about, I read the paper and then I like try to understand the model of it first, right? That's
Right.
kind of my big approach that I've taken throughout.
So what's a failed experiment or paper replication that taught you the most?
Oh, failed experiment. For sure. Uh, honestly, so like honestly, like there's a out of all of the research papers that I read, and then maybe like a third to a quarter of them, or maybe like a third to a fifth of them, are what I'm actually making a video on, right? Like it will be like let's say like 4 out of 5 of those research papers, I'm doing like experiments in Colab. I'm going through. I'm like, oh, this is a cool paper up front. Um, Let me go through. Let me experiment. Uh, the experiment doesn't work. The experiment it doesn't back up what they what they said in the paper.
Completely
Different
right.
types of things that will happen like 4 out of 5 times, and then so like, that happens more often than not. Um, with like, and like I just look at that as part of the experimentation overall, and also too within that there'll be like I look at it as um, like not failures, but there'll be times where I'll like look at or research a concept like LCM models is a big concept, right? I
Completely, yeah.
first looked into LCM models and I was like, okay, cool paper. I made a video on it, and then that ends up being like the most interesting. Like people are like so interested in LCM that like I've had to like continue and go deeper into LCM research very specifically. Like whereas it's something that I put like I was like, oh, it's just like a one-off thing for me
Completely.
originally, and it just kind of grows from there.
Right. So if you had unlimited resources, what problem in deep learning or AI or quantum computing would you like to solve first?
For sure. If I had unlimited resources, I would go all in at the moment in um, HDC spaces and combine and fusing that with deep learning, and then trying to come up with something along those levels. And if I had unlimited resources, I could experiment with that via quantum hardware, and I would combine those three things. And then my
Right.
goal would be flat out to like I would flat out want to try to solve um, the gaps in physics, right? Like I don't know if I
Right.
could unify physics as a whole, but like that's what I would want to work towards. I think like that's where we're at more. Like I look at what I do as far as researching is chipping away at our gaps in physics knowledge and our current gaps in physics, and that's where we're making huge breakthroughs, right? Like why all of a sudden are we making huge breakthroughs? Because we're chipping away at those things. Like that's why you're seeing so many things like like our understanding of physics is flawed. Well, yeah, it's been
Completely.
flawed for 50 years, but we're just
Right.
finally hammering away. But then once like that facade falls, then it's like there's a whole world on the other side. I don't know what's on the other side, but I
Right.
want to know. Like, and that's what I like. That's where I go towards. Like, what's on the other
Completely.
side of that wall?
So imagine quantum computing as a video game, alright? And what would be your final boss battle in that then?
Yeah. uh, I guess I mean the boss battle would be um, the fusion of quantum and relativistic physics. What is the ultimate answer within that? Yeah, I guess that would be the boss battle. If we could solve that, then I think we solve like every other. Like I think like there's nothing else to solve past that. Like, everything else becomes easy past it. Like literally everything else becomes easy, whether it be um, solving climate change, whatever. If we solve that part of physics, we'll solve everything else. I think.
Completely right. So can AI truly understand physics, or it will be just the pattern recognition?
That's a fantastic question. I so I think that there's like to me there's nothing inherently with what AI does that prevents it from understanding physics overall. What is lacking right now is that physics is related to physics, right? It's related to objects, to an environment, like and actually like having a body, interacting with your environment. Like I don't think you can. Uh, like I don't think you can simulate that. I don't think you can train that. Like you need a body in order to understand how physics works on a body. How like I mean I don't need to like explain to you how gravity works like or to not jump out a window because you're just not gonna do it right. You just know.
Right, yeah.
But like I mean an AI model is just gonna like it would just jump out a window like it wouldn't care like you know like
Yeah,
I
it
don't, I
wouldn't
don't know
care, yeah.
like
Right, yeah, that's really funny, yeah, completely. So, will quantum machine learning make classical machine learning obsolete, or they will coexist?
Another fantastic question to me. Like, so it's like my honest answer to this, and this is just like philosophical, right? I don't know. Like, but so I think it all goes back to that versus as opposed to like combinatorial problem, right? Like, I think that they're just two sides of the same scale. Like, it's not a versus. Like, I think that there's what we'll find is that there'll be certain problems that will be able to be better solved with quantum hardware and quantum algorithms, and certain stuff that will be better solved with classical algorithms and classical hardware, and then certain fusions that will occur and certain emergent properties that will occur when you combine those both, and I wouldn't know what those are.
Completely right. So, what's your take on the OpenAI's Sora for text to video generation, or Google's similar thing which made by Google, or all those like big tech giants who are making the similar thing? So, is that a breakthrough, or it is just a hype?
uh, I like I mean my opinion on generative AI as a whole, like I think, like my personal opinion is that generative AI is an off ramp. Like it's a stopgap. Like it's cool technology up front, but it won't be like the real thing. Like in 10 years from now, we won't like generative AI won't be the big thing. Like what it would evolve into is kind of like, and the possibility of it would be like the holodeck from like Star Trek or something like that, right? Like
Right.
where
Okay.
we can get into that type of technology, and perhaps that's the evolution of generative AI. But like, I think I'm very bearish, honestly, with regards towards generative AI.
Right. So, what's the one thing you want your viewers to remember from your work in upcoming decade?
For sure. I get. I mean, I can be have a rough exterior a lot of times, but I genuinely like it when people are genuinely want to learn and want to understand things, and and have a genuine interest in learning overall. And then so that, I mean, that's it, right? Like I just hope that people learn and
That's
get
really
inspired
nice.
to
Yeah.
learn.
So, what's the biggest misconception about the quantum computing's readiness for AI applications?
For sure. I like it's how, I mean, the biggest misconception would be like how close it is and how economically viable it's going to be. Like and like like no one knows the answer to that, right? Like, but like you have I call them the crypto bro space, where like they want it to be super viable, and then so like you talk to like certain people, they just hype it up, right? Like so that's like it's the next hype cycle is quantum, and then so according to this hype cycle, they want it to be the next big thing within 2 years, and they want all of this to happen, and like they want it to happen with 100% certainty. But uh, that's the problem with an equation, right? Is that like they might be right, but and like they're 80% right, but like there's 20% that they're not right, and 20% is
Completely.
kind of big. Like if you're like, I wouldn't bet my life on 20%. Like I wouldn't bet my life savings on 20% being wrong. Like
Right. So, what's your take on the new thing which came out recently, Deep DeepSeek AI? Is it
yeah,
similar to OpenAI's ChatGPT or is it different? People were comparing like R1 as a to O1. They are similar. What's your take on that?
yeah, for sure. So I've tested out, and like I like to do and do like I have my own tests that I do, like and my own kind of like benchmarks that I go through with the models.
Hmm.
Like my benchmarks with the model, like my like just pure honest. I try to be as honest as possible. Like I think that there's like still a little bit of a gap between O1 and DeepSeek when you break it down, right? Like when you go in,
Right.
you're like the like the fact that DeepSeek shows what it's thinking is remarkable, and it's
Right. Yeah.
fascinating, and I love it, right? But
Completely.
it
Yeah.
tends to get off track more, and so I'll use an example, right? Like so I had like I was trying to have DeepSeek like write a paper, and then like I have it go through it. I can see it's thinking, and then at first it's good, right? But then it just it's it goes like off the rails, like off the track,
Hmm.
and like it gets like a thought not related, and then it continues that thought. Whereas O1 doesn't do that. Like it's much better along those lines. So I think
Right.
like O1 is better tuned. Like if I was uh, especially like an enterprise organization, like a company evaluating these things, like I don't like I think like there's no way that I could say with a clear conscience that um, DeepSeek is the same as O1. Like there's a difference
Right.
there. Could there be like the gap could be easily closed, but right now it's not.
Right. 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 Completely. Yeah. So, how do you think that thinking out loud thing works in the DeepSeek?
Yeah, I mean, so to me, that's fascinating, right? Like, and
Right.
the researchers themselves, they pointed out as an emergent property that occurs, like an aha moment that occurs, an emergent aha moment
Hmm.
that occurs within these moments and within these models, where it's so what we're learning more. You brought it up before, like classification theory and breaking that down, right? So classification theory, within that, all you do is you're just taking like a larger problem and then you break it down and you crunch it into smaller and smaller problems. Um, and then the logic is that's what our brain does. That's how we think, right? And then we do that, and then like it's fascinating that it works. So
Right.
to me, it's true. Like it seems to be like that's true. Like that seems to be how our brain works. If I'm not anthropomorphizing, which I could be, right? I'm always like I try to be very careful about that. Like, am I anthropomorphizing here? I don't want to be, but I don't. It doesn't seem to me like it is. Like you have the emergent property, you have the aha moment. It thinks through, and it can, like a human, go off the rails with its thoughts too, right? Like but it's to me it's a replication of human thought in that instance. It seems to be.
Right. So, what's your litmus test for judging whether the paper is worth implementing or it's just like you're reading and hopping to the next one?
Yeah, that's a good question. To me, uh, first, the first litmus test that I look for is is it personally interesting to me?
Hmm.
And there'll be like a lot of interesting, like a lot of research papers where like people are hyping it up, and then if it's not like interesting to me, I don't, I avoid it. So if it's like in a space I care about, and then the second thing is so I'll go through the paper. How well structured is it? Like, exactly is their argument? And then, do they provide like code backing within it, or like experimental backing within that? It's kind of like the third thing. And then like then I go through it, then I experiment with it, and then how well my experiments go through determines where I go forward from there. Honestly, so that's my progression.
Right. The Quantum AI Fusion Roadmap 2030 named paper predicts that hybrid systems will solve NP hard problems. Is that realistic or it is overly optimistic?
Like so I think it's hard I think it does anyone a disservice to speak on these things with certainty, right? Like I can't say with certainty that we will solve that, that will come to fruition. I think it's 80%, yes, like 80%, like absolutely will be able to solve hard problems that we have like no business solving today, and we'll be able to solve them by 2030. But it's not 100%. Like it's not like I could be wrong. We could all be wrong. There's still gaps there. It's we're still not there, right? Like if we were there, then we would be having a different discussion. And then so because of the fact that there's still gaps that exist, no one can like fully look past those gaps. Uh, like will the sun rise tomorrow, right? I mean, yeah, the sun's gonna rise tomorrow, but I can't tell you 100% that it's gonna rise tomorrow.
Right. So, uh, what AI, like, what sci-fi movie that you think our future will be looking like? Like Cyberpunk or Blade Runner or which one? Like, you are into games and movies, so yeah, that's why I asked this question.
Yeah, for sure. Um, I don't know which I don't know on it. Like I guess Matrix, like the Matrix series is seem like there's a lot of prophetic things within the Matrix series. I don't want our society to come out that way. Like
Right.
Matrix is what I would not want, but like I guess like that's what I lean the most towards, if I'm being honest.
Right. So, if quantum AI fusion enables super intelligent systems, could they rewrite their own error correction protocols and become self-evolving entities beyond human control?
That's the big question, right? Like, so I mean, so to me, like once we hit that's ASI, right? Because that's like once it's self-evolving, like it's self-evolving. Uh, there's nothing that would stop. There's nothing mathematically preventing that. And there's nothing hardware-wise preventing it. Uh, there's algorithms that are very close to doing that. We're like experimenting more and more with that. So I think that we'll have. I think we'll crack self-evolving algorithms before we'll crack quantum computing. I feel comfortable saying that. Like I think we're closer with self-evolving algorithms than we are with quantum computing, which might lend themselves hand in hand, right? If self-evolving algorithms solve themselves, then we probably solve quantum computing shortly.
Right. So, will quantum neural networks develop consciousness by exploiting superposition to mimic biological brain states, as speculated in quantum neuroscience? So, normally we think that the consciousness is not exactly what it is in a human brain and the like neural network. We think it is as a just mathematical shape. So, what's your take about that?
Yeah. I, I mean, I do think that my philosophical opinion on it is that there is most likely a correlation between quantum superposition and consciousness, what it is, I don't know. I don't know what the correlation, the direct correlation is, but uh, like the way that neurons work, the fact that information passes past nerve cells, our past nerve walls, like uh, that can only happen via quantum superposition. There's no one else can give me an actual explanation for that. So
Right.
I have to assume that that's what occurs, and then so I have to assume that there's a direct correlation between the two. Um, I like correlation doesn't mean causation, so I don't know if there's causation, but there's definitive correlation.
Right. So could quantum enhanced AGI bypass classical encryption, triggering quantum singularity, where all physical security collapses overnight? Is that possible?
I like yes, it'd be like if I answered that question no, if it's not possible, I'd be lying. Like there's a possibility that that could exist, and that could happen. It's a low possibility, and I think that I don't think it will happen overnight. Within that, it will be a progression, and we'll have warning signals before that happens. And then like
Wow.
so, what I will say, like we're starting to have warning signals right now, right? Like
Right.
we can solve simpler quantum algorithms than what we utilize. Um, so our quantum algorithms will fall, but we'll know before they fall. Like it won't just be like, oh, tomorrow we'll wake up and they're gone.
Right. So if logical qubits uh, achieve fault tolerance, will quantum networks form quantum internet, a parallel reality where data exists in the multiple timelines?
uh, so I mean that like I don't like that depends on what the specific solution is to physics with regards towards time. And like um, I don't know yet. Like so we're like experimenting with like time series algorithms and things like that, and
Right.
you can like there's theoretical probabilities that that's probably the case, but like I don't know. Like we don't know enough about physics yet to say
Right.
definitively if
So
you could do
what
that.
do you think about the mind upload concept, the whole concept?
Yeah. So I mean, going back to what I said earlier, I fully at this point think that the mind is a computer basically, right? And that the universe computes, and then so I think that nothing there's no barrier beyond just knowing how to do it and us inventing the technology to be able to do things like that. Like it would just be um, just uploading to another format. like and um, I have like proven at this point so I can showcase at this point that you can like say for example take like an audio file and you can convert that audio file to straight up binary, so like just zeros and ones in machine language, and then convert it back into audio and play it just like with zero loss in the audio. So you can take audio or different file formats and convert them into just flat out binary, and then do that. So um, I don't see anything that says that brainwaves would be different. You just convert it to
Right.
binary and there it is.
So there will be nothing like quantum inspired algorithms creating the digital versions of humans in the entangled qubit states.
uh, like that's a scary thought.
Right.
Like I mean, that's within a realm of possibility that would exist. I would say
Right.
I generally utilize like Occam's razor when it comes to these things. So um, there so that possibility is within the realm of possibilities.
Hmm.
Uh, Occam's razor says that it's probably not the most probabilistic probability, but it's a probability that exists.
It isn't right, yeah. That's scary thought completely. So, will quantum computers decode alien signals hidden in the cosmic microwave background noise, revealing the galactic quantum network or something like that?
For sure, good question. Um, I think so. So I guess that this is a like Fermi's paradox, right? So I come down on the thought I think there's aliens have to exist. Like the universe is very vast, so the aliens would exist. And then so the only reason why we haven't communicated then with aliens is either that it's too vast, expanses, or our communications are like not scientifically advanced enough at this point. And then so it's probably that, like it's probably a mixture of both. And then so if we get more scientifically advanced communication, then we'll probably have a higher
Completely.
chance of communicating with aliens.
Right. So yeah, there was one crazy question I used to have. So if quantum simulations map black hole insides or interiors of black hole, will we be risking creating artificial singularity that will like devour Earth itself?
Uh, I mean, say like, yeah, I like that's the crazy thing to me when it comes to some of these experiments, right?
Right.
And so with some of these experiments, if you ask that question, the probability is more than zero. Like it's I mean it's in some instances it's like zero, it's 0.00, like two magnitudes of extreme, but and then a one, but it's often more than zero, right? And then so yes, like with a lot of these experiments, that could be the case. Like the probability of that being is more than zero, but magnitudinally lower than like even like 1%.
That's really awesome. So how, if anyone wants to talk with you or contact you about the things that you teach or they have any doubts, then how can people approach you?
Yeah, for sure. That's a good question. The best, like the easiest route to get a hold of me is via like LinkedIn, or like on my YouTube videos. Like those are the two channels that I check the most frequently. Um, but like I generally am open to communication. Like just feel free to reach out.
Right,
I don't like I'm not on like socials a lot, but like LinkedIn and or
right.
YouTube are the big ones.
So people can directly comment on your videos and ask the questions whatever they have.
Yeah,
So
absolutely. Yeah,
that is
absolutely,
a really nice
absolutely.
thing.
Like LinkedIn, if you want like a more direct response, just being honest, like
Right,
you'll get like almost guarantee a response from me from
right, right, right. That's really awesome. So it was really nice to talk with you, and
LinkedIn.
hopefully next time we'll talk as well with some different new exciting things with all
Absolutely.
these crazy topics. It was honor to have you on the podcast, man. Thank you for your time.
You too.
It was
Likewise, for
really
sure. Have a good one.
nice. Thank
You
you.
too.
So yeah, I stopped the recording, man.